Hi, everyone. My name is Paul, and I'm presenting on behalf of the Invisible College team our private voting hack using AZTEC for the Gitcoin Protect Privacy Hackathon. Briefly, as an overview, I'll talk about private voting, how to achieve it on Ethereum and why, and in the context of DAOs, why voting is important and private voting can be useful. Then I'll talk about AZTEC, the ERC 1724 standard for confidential tokens, and the join split primitive, which is how it achieves privacy on a public blockchain. And I'll give a web demo called ZK transfer, and then the command line demo, which is the backend chat, which coordinates the web demo. It's called dark chat, which is an end-to-end encrypted chat with no signups. And then I'll talk about our algorithm, which is not implemented yet, but it will tell you how to build private voting out of the basic building blocks of ZK transfer with AZTEC. And then we'll talk about future improvements and wrap up. So let's get started. First, a quote from the father of voting, the Marquis de Condorcet: "Enjoy your own life without comparing it with that of another." And we'll adapt that as our motto of as enjoy your own vote without comparing it with votes of others in an election that you trust. So without comparing it with others means you don't care of, you don't know beforehand about the outcome, and you also don't know who voted for what. And an election that you trust, as will become evident, will be a trustless on-chain mechanism. So what is private voting? To start with, we'll define that registered voters in a permission system are eligible Ethereum counts, whose opinions you care about. It could be token holders of your governance token. It could be anyone in your DAO. It could be just a subset of people that you know in real life. So a specific example of a proposal that you can vote on with binary options you vote yes, no on is an election. For example, the US presidential election in 2020. You have multiple candidates and you can only vote for one of them, and that will be marked a yes vote, and then all the other candidates you interpret as a no vote for. Each eligible voter, citizen of the United States, gets a ballot, and if this were on Ethereum, they would submit it on chain before the deadline, let's say November 8th, 2020, to get counted. Here we'll note there's a quantity called verifiability, which means are the votes counted correctly, and this derives from transparency in the traditional Ethereum model. It was one of the original use cases. A Solidity example contract on the front page of Ethereum was voting. So everyone knows how everyone else voted on the public blockchain, and that's how you can make sure that the votes are counted correctly. And that's also how a lot of DAOs work currently, but we can actually go beyond that. So why do we care about private voting? Well, arguably the goal of voting is decision-making that creates the best outcomes for voters. So anyone who has tried to choose a movie to watch, let's say Hamilton in the past weekend on Disney Plus, or ordering food at a restaurant, which happens a lot during quarantine, or even voting, again, for the aforementioned president, seeing what the majority of people prefer, especially your friends, can influence you away from your true preferences for whatever reason. In the short term to fit in, and then in the long term, it's not what you want. So DAOs usually want the users to vote their preferences honestly, and especially to elect leaders. That's why voting booths have a curtain. You don't want anyone to watch you vote, so you can vote who you really want. But then when you go home, you want to trust that the machines will actually do what they say that they do. But once the leaders are elected, usually want your leaders to vote transparently. So in the US Congress, you want your congressperson, their voting record is available for everyone, and if they don't meet their campaign promises, you want to be able to call them out on it, or journalists be able to report on it. So private voting isn't all flowers and sunshine. There's dark DAOs. So if each user's votes are concealed from the public, but could be revealable to private donors, this could actually scale up the practice of automated vote buying to be much worse than the manual problem in real life. And there are other downsides, but I'm biased and bullish towards private voting, so I'll move on from here. So voting in DAOs, decentralized autonomous organizations, usually in terms of sustainability, want decision-making to be guided by the user. So for exchanges, it may be whether to list a trading pair. For MakerDAO, which is one of the longest running DAOs and the one that governs the largest store of value, which is the DAI stablecoin token. It's extremely important. Every week, an executive poll with various measures is voted on. And if you hold the governance token MKR, you lock it up in a contract, and then you're able to determine whether these new parameters take effect or not. And currently it is in the open, so you can tell which address votes for what. Why do we choose AZTEC? So let's briefly talk about other privacy schemes. The simplest kind is called commit reveal. You could just use a hash like Ketchak 256. And this means that you hash your plain text value, which could be yes, no, 0, 1, into a hash, maybe with some blinding factors so you don't just have two options. And then you commit that on chain, and then later, after the election is over, you reveal, maybe also on chain, consuming gas, and people verify that the value you reveal, in fact, was the pre-image of the hash that you committed to earlier. And this has the disadvantage of it taking a second step. There's also a technique called blind signatures. There's a blog article online, which unfortunately I don't have a link to now, of how to ensure private voting by blinding each signature or applying these randomized factors. And this costs about 500 to 600K gas per vote. So it was the first or the earliest result that I know of, and it's impressive. It does provide complete privacy, but it is expensive gas-wise. And as far as I know, you can't batch things together for more efficiency. There's something called ZK Starks, which is an alternative to private asset transfer. As of this writing, or the last time I checked, it was only on testnet and of comparable price to AZTEC, but also an interesting technique that I know less about. And then Gitter is another way of encrypting Ether, and this is implemented as an experiment on the private Quorum blockchain by JP Morgan. And I know less about that, but also an interesting approach. So the advantages of AZTEC is sometimes called the SSL of Ethereum. That's a wide-reaching claim that kind of implies that it can encrypt any transaction, just like HTTPS or TLS can encrypt any web request. In our case, it has a good start. So it's encrypting basic operations, not general ZK snarks, but specific operations related to finance, financial applications, and asset transfer. It takes about 200K gas per on-chain confidential transaction. After the Istanbul hard fork, there's some precompiled elliptic curve math, which it now provides cheaper access to. And AZTEC can be amortized across hundreds or thousands of votes. So this 200K gas is actually, you divide it by 100 or 1,000 votes in elections. The upper limit has not been tested, at least not by me yet. The AZTEC team probably knows how far you can take this. And it's been on mainnet since November 2018. But they had a trusted setup recently, so you don't have to rely on their published trusted setup. I participated in the ceremony a few months ago, and there are a lot more parties, stakeholders now, to ensure AZTEC's future. So what is a timeline like in our voting example, which could be private? So step one, users register their weight, the weight they carry in an election. So this could be locking up MKR and MakerDAO's voting contract. It could be acquiring reputation in a DAO like DAOstack or Moloch. It could be just registering your accounts with a election commissioner, like a normal off-chain bureaucratic DMV that you show up to and register to vote. In this case, we refer to an election commissioner, or it could be a bot, just an administrator that carries out coordinated activities, and you do not have to trust it if it runs in code. You can everyone can verify that it acts correctly, but it will handle information and relay votes and things like that. And we don't believe it causes any problems, but that's open for feedback. Step two, the voting period begins, and this is recorded on chain. Step three, users submit their votes after a deliberation, and they also do this on chain. This consumes gas. It can you can batch them together possibly for efficient savings. You can sign your votes with a scheme like EIP 712, and then you can relay these votes to other people or to the election commissioner bot. And this is one way you could batch things together instead of everyone submitting on chain themselves. And here's where you commit to a private value if you're using a commit reveal kind of scheme. So the voting deadline passes on chain in step 4, and then in step 5, votes are counted. So then the results committed on chain in perpetuity, so that everyone can verify what the count was. And this also consumes gas. Again, step 2, 4, and 5 consume gas to it could be encoded parameters encoded into the original contract, but it's not a lot of gas, and the bot of the coordinator handles it. The most gas is in step 3. But in step 5, the results could be integer or Boolean. You can know by how much an election was won, or just a simple yes/no, like did this person get more votes than other people or not? And either of those could be coded into your contract, depending on what the desired result is. And if it's a Boolean, you can keep it a secret what the range was. But what is kept secret in our definition of private voting is who voted for what. So now let's go to the web demo. The URL is zk-transfer.netlify.app. I'll probably say it a few more times, but the link is available in the video notes. This is a beautiful UI designed and implemented by Joseph, our teammate, who is a React and front-end wizard. So it is a built-in wallet for zero-knowledge assets. And you can see balances, which are 0. So it's things aren't hooked up to a blockchain yet, but they will be in future versions. Here you can list these confidential tokens, the ERC-1724, alongside plaintext tokens if you're ERC-20s. And if you had a balance, then you can send them. So you could type in a value of, these are the trading symbols of the tokens. We don't really have Gnosis, DAI, or MKR, but you get the idea. And then if you click send, step 2 in this column is you can choose from what users are online. And you can send it to Uncle Vitalik. He definitely needs more digital assets. Or you can send it to other people who happen to be online at the same time. These are hard-coded, but the eventual goal for this demo is to give people firsthand experience, like a playground to try out zero-knowledge techniques. And here, users would appear and disappear as they were online. So if you were to open, for example, this new tab in a different browser, or a friend would open it at the same time, you would see their screen name appear here. And rather than exchange Ethereum addresses or AZTEC public keys manually, like you would have to do in plain text on Slack or using Signal, which is a totally separate messenger, we coordinate users exchanging this information and also zero-knowledge keys in an encrypted, private way using dark chat, which is our own chat server, which is the next demo. But the importance here of end-to-end encryption in chatting, for which no one but the users have keys to be able to read it. So, WhatsApp, Facebook Messenger would not qualify for that either, and perhaps not even key-based. The importance of that is that AZTEC stores value in notes, which are like unspent transaction outputs for Bitcoin, but in this case, it's for Ethereum tokens. So all the ERC-1724 values are not just balances. It's not just a number as in the ERC-20. They're actually like notes, and you have to keep 2 related secrets for the meaning to be that they belong to you. One is the viewing key, and that's so anyone can verify the value of the note. And then the spending key, which allows you to transfer the note to someone else of equivalent value, new notes of equivalent value of the same tokens. And if anyone knew the spending key, even the server that was coordinating this, like our web server, Netlify, for example, or whoever was running the chat server, if they could see you exchanging the spending key, they would effectively own your notes, which is where end-to-end encryption is necessary. And then finally, after you choose a recipient, some waiting time is involved. And that's much faster than it would be on a real blockchain, but hopefully not too much faster. And then in this transaction list, you would see transactions, assets that you receive would be the down arrow, because you sort of like receive these zero-knowledge notes, these secrets from other parties, and also a transaction hash from the blockchain. You could send them out, so this is you sending them, and that's uploading them in some sense to the blockchain, or sending these secrets to the recipients that you're sending these assets to. And then links to open it in Etherscan, as you would expect, the amount of the transaction. And this part only you can see, because you're one of the 2 parties in this transaction. And this is the part that AZTEC would keep secret, not the parties themselves. Other people could tell the 2 Ethereum addresses it's transacting, but but not this value. And then if it fails, this red X. So that's the web demo. We encourage you to try it out. If you want to know what the generated Ethereum address is, here you can open the web console. A lot of things are runnable there. This is this address, but you'll have a different one, of course, and there's nothing up our sleeve. You can make sure it actually works. And this will become much more smooth in the future. So let's move on to dark chat, which is the way these things are coordinated. So there are 3 screens we'll look at for dark chat to verify that we're actually getting encrypted chat. And this was worked on by GD and coded from scratch. We initially tried to use Ethereum Whisper, but we couldn't get 2 peers to communicate. So everything had to be connected to the same node in our experience for messages to be passed. And that was less than useful and kind of defeats the decentralized, sustainable, like the mail cannot be stopped Pony Express kind of spirit that we were going for. So GD, wrote his own server in about a day or 2. I think stayed up overnight, and then together we added encryption support, and it's great. It was a lot of fun. And here are the things that we implemented with it. So there's a dark chat client, and what we would like to do, this client could be this web app that we just saw. And here I'm going to actually remember to switch my open broadcasting studio. Okay, so I know it looks like a bunch of text. And what we want to do is coordinate. So this client is going to request from the coordination bot, the administrator, can you please give us some Ether just so we can run some transactions? That is one of the onboarding challenges, that new users have empty wallets, and meta transactions is an elegant and a beautiful way to solve that. We haven't implemented that yet, and so for now we actually just request a small amount of Ether from the bot. And the way that request looks is it's a chat message. So the chat it's interpreted in a particular way by bots, but you can say anything to the bot. You can say good morning and sing songs to it. In this case, you're specifying it is a go back. So this value here, you're specifying it is a private message to the bot's public key, which is this. And this is a key pair on the same elliptic curve that Ethereum uses, SecP 256K1. And you're sending a command here, top up, which just means I want to fill up to 0.1 Ether, Rinkeby Ether. All the demo currently runs on the Rinkeby testnet. And then finally, this is the address to send it to. So this is the address that you saw in the web console. So we're going to copy this. And here, Darkbot is just pinging us every 5 seconds to let us know we're live. It's a public message. Dark chat supports both public channels and private messages. Okay, so it is still pinging this heartbeat, but here in Darkbot, and I'll highlight what we should be following here. It is mining this transaction. And it retries every couple of seconds. It succeeded, so there's like error, but it's more of a warning just to keep the demo spicy. And what we expect to see if we were to switch to Etherscan is Rinkeby Etherscan rather. So again, this is the client. This is the user of the wallet who is requesting from the bot. And the address would be here. And here you can see it does indeed have 0.1 Ether, and it was mined 58 seconds ago. There we go, yeah, 58 seconds ago. Okay, that's pretty good. And then the third view that we want to see in the dark chat server is here. So these are log messages, and this is a centralized server. It could be run by an adversarial party, and you can see that it sees in plain text all these messages that say darkbot lives. This is on a public channel, and this is just a heartbeat for everyone to know the bot is alive. It seems like fairly safe knowledge to advertise, but here is a message from me as a user, as a username CryptoGoth, and it's sending this long hash. And this is actually a AES encrypted hash in counter mode or CTR mode, and it uses a symmetric key, which is recovered as a shared secret using elliptic curve Diffie-Hellman exchange. So the key pairs, the public keys for the bot and each user can be combined to recover a shared key, and then that's used to seed this message. And as you can tell, it's not human readable. You actually don't know what the amount requested was. You could look on the blockchain, but this is actually a test case. So later when we actually share ZK note viewing and secret keys, that also would not be viewable from even the server coordinating the transaction, which is pretty cool. Oh man, I forgot to switch this over. Okay, sorry, I'll do this again briefly. So this is the chat server, and all the messages, darkbot lives every 5 seconds. That's in plain text. But this message here, which was the request to top up 0.1 ether, that's a long string of hex, as I mentioned, AES encrypted, recovered from the shared key, blah, 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 blah. And that's it. Let's go back to the presentation. Okay, so what might an election look like? And, let's say the United States is electing their president in 2020. And let's say there are three choices. There's Biden, there's Trump, and then those are just placeholders. Actually, the people really hunger to vote for Vitalik Buterin, and they have various platforms, and you can consider them. When it comes time to vote on the election, what does it actually look like so that you can vote privately on chain, and then also have a verifiable count so that you don't actually have to recount paper ballots or trust Diebold or refer to the Supreme Court again in battleground states. So this is going to be covered really quickly. There's more details in a Stack Overflow answer linked here, but these are the various steps from the timeline before. When you register to vote, you can be selected from your on-chain token holdings. Eligible token holders, or again, you can register at the DMV. The election coordinator bot, EC, creates 2 tokens per candidate. One is for yes votes, one is for no votes. And in our example, there are 6 ERC 1724 tokens. There's Biden yes, Biden no, Trump yes, Trump no, Buterin yes, Buterin no. And each voter is granted a note of random value. The range of ERC 1724 tokens is from 1 to 1 million. So for each token, between the tokens for each candidate, the value is selected at random, but between the yes and the no tokens for the same candidate, they are deferred by 1. And this is a measure to simply prevent people from validating a 0 value or a 1 value. So in case the vote is intercepted, this is a feature of the AZTEC contract. It lets you validate whether a potential future spending transaction would work without being the owner. And so if you were able to intercept someone else's vote, you just try out spending to 1 vote or spending to a 0 vote to figure out whether it's yes or no. And so that measure handles that. And there are more details I'm going over very quickly right now. It's still the algorithm design phase, but we want to hook it up to the web UI using the dark chat command line UI that you saw earlier. So number 2 is cast the vote. They would use something like the web UI, and the recipient of votes would be people listed as a Biden yes vote, Biden no vote, so on and so forth. And then finally, when the deadline is over for the election, the votes will be counted, and the election coordinator bot would act in place of these candidates, of Biden yes, Biden no, Trump yes, Trump no, and it could do what's called a private range comparison. So it could compare whether the number of Biden yes votes was more than the number of Trump yes votes, for example, and just do pairwise comparisons. And then from that determine whether who won the election. And since the election coordinator bot issued the tokens in the first place, they know what the total valid number of votes is, and they know what has to add up. And what people can trace publicly is who voted. So what is public knowledge is who is a registered voter, which Ethereum addresses are registered voters. So in that sense, this mechanism requires a little more study, but that is the general scheme of the vote. So this is our team. I'm CryptoGoth. I worked on the back end and algorithms. This is Joseph. He worked on front end and React. And this is GD, and he worked on dark chat. The biggest feature improvement is to move on to XDAI. As you saw before, 200,000 K is still pretty expensive. It ends up being, I think, $20 or $30 at current gas prices. If we moved on to XDAI, it would be fractions of a cent, and that seems like a pretty good deal. So thank you for listening. We had a lot of fun working on this hack. Here are links to our GitHub repos. Again, the link to our web demo, which we encourage you to try. And also, we'd love to chat with you on Gitter, so you can drop by, let us know what you think, request features, report bugs, give us venture funding. All of those are welcome. Thank you very much. And we look forward to hacking more with everyone online soon. Goodbye.